Okay. So that is part 1 of chapter 2. And you guys online, you guys have questions? Are you guys okay so far? I'm going to let you work on stuff after this. So after we do a little bit more here, the reason also I have to go through some stuff is that on Tuesday we have there's a professional day, and so formally classes are canceled. In other words, you don't have day classes. I will have office hours on Thursday, and so so as a result, because we have the concept check this weekend, the only thing that could be in the concept check that we haven't done is this idea of singular and non-singular. So that's the one thing that's on the concept check. I think that normally we'd have more time to go over it and review it, but that then you've just learned it now, and so you want to sort of remember that you want to know how to solve that, what we just did. Okay. So there's a little bit different point of view with the second part here. Let's see, yes, okay. So in part 2, the focus is again on a pattern rather than a procedure. It's on, the focus is looking at linear systems with the same solutions. The idea is this. Here is like a possible coefficient matrix of a linear system. Now, if we did echelon form to this matrix, we could do -2 row 1 plus row 2 and get this one, or we could probably take this one and divide it the first row by row 1 and get this one, and then if we could add row 2 plus row 1, we could get this one. So all of these 4 matrices are all connected by row operations. Therefore, they all have the same linear system. So you can imagine, well, which linear systems all have the same solution set? Because there's a whole bunch of them that have different, in other words, here's 4 of them that all have the same solution set. And you can see that I could do lots of different row operations and get lots of different matrices that would all have the same solution. And now here's sort of the context of what we're going to do, or what the point is. This is an analogy, okay? You know that there's fractions, right? 1/2, 3/8, 4/7, all kinds of fractions, right? But you know that some fractions have the same value as other ones, like 1/2, 2/4, 3/6, 4/8, and here 3/8, 6/16, or 4/7, 8/14, 12/21, right? So all of these have the same numerical value. These have the same numerical value. These have the same numerical value, right? So we all say, well, these all have the value 1/2. So we sort of think of this value as 1/2 as special because I've canceled all the common factors. I say, you have this problem. Okay, take a fraction, reduce it to lowest common denominator. Well, each of these always has one number that's a unique special. You can think of this as the name of this class. You can think of this as the name of this class, and this is the name of this class. So we're going to look at linear systems the same way. Think, okay, we have a whole family of linear systems that all have the same solution, except the same numerical value. It's the same solution set. So we have a whole bunch of linear systems that have one solution set. Another set has another solution set. Another has another. Is there something unique that represents sort of like the 1/2, like lowest common denominator for fractions? And it turns out there is. And so what it turns out is it turns out to be the end result of what's called the Gauss-Jordan method, which is an extension of Gauss's method. Okay? So the goal of Gauss's method is echelon form. The goal of the Gauss-Jordan method is reduced row echelon form. And it turns out if I take any matrix that has the same solution set and make it into reduced to echelon form, that reduced to echelon form will always be the same. This thing is unique in the sense that it's like the 1/2. It's like reducing fractions to lowest common denominator. If you take two matrices and reduce them to reduced to echelon form, and those are the same, they have the same solution set. So it's a way to tell, are these two matrices equivalent or not? Okay, so we need to learn this Gauss-Jordan method and learn what reduced to echelon form is. That's the context of this second part. So there's a procedure here that we're going to go and focus on. So let's just take a linear system, 2x plus 3y, but maybe one that's not, maybe I should do one that's not so complicated. Let's just do x plus y plus z equals 1, and say x plus z equals 2, and x minus y plus z equals 3. Okay, so here's a linear system, and we're going to now, from unlike chapter 1, now we're going to go forward, and like in assignment 2, everything's we're going to do with augmented matrices. So we're not going to use equations anymore. We're always going to go to, so we first change this to the augmented matrix. 1, 1, 1, 1, 1, 0, 1, 2, 1, minus 1, 1, 3. Well, there's the augmented matrix for this linear system. Okay. Okay, you guys okay with this? So then I want to solve this. I want to reduce it to echelon form. So I'm going to do minus row 1 plus row 2 and minus row 1 plus row 3. I can do this because this one affects row 2, this one affects row 3, so they don't affect the same row. So I don't have to worry about any interference of one operation with the other. So I don't change row 1 up here, but I do minus 1 plus 1 is 0. Minus 1 plus 0 is minus 1. Minus 1 plus 1 is 0. And minus 1 plus 2 is 1. That's the first operation. The second one is minus 1 plus 1 is 0. Minus 1 plus minus 1 is minus 2, and minus 1 plus 1 is 0, and minus 1 plus 3 is 2. Okay. So there's my doing that. Hopefully you guys are okay. Then I can go, I'm going to change this to another system here. Let's think we want to do. Well, we've cleared the first column. That's the goal here, because we're making progress toward echelon form, because we need to get these to be 0. Now we can get to echelon form if we can get this to be 0. So we need to do minus 2 row 2 plus row 3 to get that to go away, right? So I have 1, 1, 1, 1. I don't change row 1. I don't change row 2 because I'm just affecting using row 2 to get to row 3. So I do minus 2 times 0 is still going to be 0. Minus 2 times minus 1 is 2. 2 plus 2 is 0. And then let's see. I don't want a contradiction here, but I'm going to get, I'm going to get minus 2 times 0 is 0. And so I need minus 2, minus 2 plus 2 is 0. Oh, I did. Oh, I'm glad. Okay, I didn't want to get a 0 there. I didn't want to get a contradiction, because now, okay, so this is an echelon form. Now, maybe it's not the best example to go to, but then what I want to do is, what Gauss-Jordan does is it wants to go back up and make and do two things. Okay, here, every leading variable has a 0 underneath it. We need to go from the bottom upwards and ensure that every leading variable, that's coefficient here, also has a 0 above it. So here, what we have to do for this is we need to get rid of this one here. Because this is a leading term, so we need to get rid of that one. So we're going back upwards and we're going to make a row operation, row 2 plus row 1. Okay, so if I do row 2 plus row 1, that's going to give me 1, 0, 1, 1, 0, minus 1, 0, 1, and 0, 0, 0, 0.
The first row is 2 at the very end.
Excuse me? Oh, yes, good, thanks. This is going to be, yeah, thanks. This is going to be 2 here because 1 plus 1 is 2. Okay. Yeah, I can go too quickly here. Okay, now this is almost in row echelon form. Also, the leading coefficients must be 1. Leading coefficients equal 1. So I can't have this minus 1 here. I have to make that into 1. So I can do that minus row 2 to have 1, 0, 1, 2, 0, 1, 0, minus 1, and 0, 0, 0, 0. So now, so every leading term has zeros above and below it. It doesn't matter about this one because I could have a 1 here because it's only the leading term. So we'll see some more examples. And the leading coefficients have to 1. So this is in reduced row echelon form. Shruti.
So we go into echelon form, but in order for it to be in reduced row echelon form, every variable has to have a 0 above it.
Every leading variable has to have all zeros above it. So that basically any leading variable has nothing above it. It's like the only variable in its column. Okay. Now, what does that mean? If you think about the equations that result from this, this means that no leading variable is, if I wrote these down as equations, no leading variable is going to appear in any other equation. What this does is this does using row operations, essentially does back substitution. Essentially does the same thing, but in a different, it gets rid of those things. So let's translate this back. There's no back substitution, right? What I can do is I just read off the answers. If this is X, Y, Z, and the constant, this equation here is Y equals minus 1. That's the second one. The first one is X plus Z equals 2. So all I have to do is move the free variable to the other side, and I'm going to get X equals 2 minus Z. There's no Y here, so I don't do back substitution. I just read off the solution. So then, let's see. New page after, okay. So therefore, then I can write down then the solutions here as X, Y, Z equals 2 plus Z, because I have one free variable, so the solution is always going to look like some vector plus Z times some vector. So I have 2 minus 1, 0, and then for X, I have a minus 1, 0. Where am I? 0. 0, and 1, because this is the free variable is z equals 0 plus z equals 0. I'm sorry about that. What's weird is there's a little bump here. Oh, there it is. And the cursor went up, but I perceived it as being on the page. It was weird. Okay, so sorry about that. Okay, so therefore our solution set here is 2 minus 1 0 plus z times minus 1 0 1, such that z is a member of R. And just to go back to the first step, we can see here's the particular solution, because that would be given by z equals 0, and the solution of the homogeneous part would be z minus 1 0 1, such that z is a member of R. Okay, this is just sort of the result of part 1 for understanding the pattern. But so we need to go practice the Gauss-Jordan method, reduced to echelon form, and then reading off the solution. But the end, reading off the solution, you end up with the same thing you'd end up with. So it just cuts out back substitution. The advantage is that reduced to echelon form, if I take any other 3 by 3 matrix, it's only going to have this solution set. This solution set will only appear for matrices that this is its reduced to make form. And it's going to show this is unique among 3 by 3 matrices. So if I take any other matrix and I wish to make it into reduced to echelon form, if it looks like this, it has the same solution set. If it doesn't, it's going to have a different solution set.
So can I ask a question? It's about this problem that I encountered on regex.
Okay.
So there was an augmented matrix, and not every leading variable
Okay.
had 0.
Let's see. Well, maybe we should look at that. Let's see. Which maybe can you recall?
Oh, I'm sorry. I misread that. It's not. No, it's totally fine. It was a free variable that had a non-zero above it, but we're just talking about free leading variable.
Yes.
So,
Yes.
okay.
So let me go give an example of what you were talking about. Though, let's look at some matrices and see whether they're in. Let me see. 1 0 1 1 0 1 1 1 1 1 0. So now let's see. Oh, listen to this. Is this in reduced to echelon form? Make a decision, and when you've made a decision, raise your hand if you're online or in person. You have an opinion when you have an opinion. It's free. I won't call on you. So, okay. So it turns out that this is not reduced to echelon form, right? Why? Did you want to answer?
Well, in the first row, you have the leading variable there, but then in the
It's not even an echelon form.
it's not even an echelon form.
Okay, so I see that. So let's put that now. Okay, so it's not even an echelon form there. So can't even get one an echelon. It's not the question whether it's in reduced to echelon. Okay, it's not a reduced to echelon form, but it's not even an echelon form. So let me try to redo the problem I'm trying to get for you. Yes, 1 0 0 0 0. Let's see. Okay, this is an echelon form. Is this one in reduced to echelon form? What do you guys think? You have it, okay, so it is. Yes, it is in reduce. Reduce. Row echelon form. Because this is a leading variable, so it has zeros underneath it. This is not leading, and that doesn't matter whether there's, like, this is not leading, so there can be a zero in here. This is leading, so it has to have zero here and here. Okay, let's see, let's try another one. Let's try 1, 1, 1. Well, let me add another. Okay, is this one in reduced row echelon form? Okay. 3 people have opinions.
Is there even treating third column of the first row?
Oh, yeah, there's a zero there. Hiding one off, I could put one in here to make. It's not even a matrix, right? It's got missing it. Okay, so this one is also in reduced row echelon form. Because this is like X, Y, Z, and W. So X, Y, and Z are leading, so they'll have to have zeros everywhere. And this is a free variable, so they have constants. Okay, now here is, okay. So this is going to be a 3 by 3 matrix. Now, here's a question. Let's say that this matrix is non-singular. And it's non-singular and in reduced row echelon form. What is the matrix? There's only one matrix, so what is it? So write down if you have an idea, see if you can write down the 3 by 3 matrix that is non-singular and is in reduced row echelon form.